You see? Okay, this is the lecture. Before going to lecture, it is good to go to the canvas and go to the canvas and go to the aerospace fluid mechanics. Everything is available in canvas. So every communication will be done by canvas. But if you have any comment or question with me, you can just text me on Discord. I later put an announcement on my mobile phone on Discord, so you can be in touch with me in Discord. But we don't have any channel in Discord. Everything will be on Canvas. So I always taught this class, but with the previous student that I taught, the class was, they were aerospace students. So for aerospace students, this class was obligatory. So it is a lot of pressure for them because it is like your fluid mechanics, like your statics for them. It is an obligatory course for them. But for you, it is an optional course. So as it is optional, the aim is to make you familiar with the aerospace, especially aerodynamic concept, and mostly on airfoils and wings. So the aim, we start from very, very basic discussion, and we proceed to finally find the lift and drag over an airfoil. Airfoil is a cross section of the wing, and then finally wing, 3D wing. So it is our main goal that last semester, some of you have a class with me, and we make a glider, we make a 3D printed airplane, but we didn't design that wing. So in this course, the aim is to reach to the design. So you know how to choose your section of the wing. So I want you to be relaxed. In this is not a very let's say tough class for you. It is just I want to make it fun for you, and at the end you learn how to design an airplane or wing. Airplane, if we consider this as an this is the vertical tail, this is the horizontal tail. So this airplane can fly by its wing. So our course is called Aerodynamics. So what does this come from? This course is part of course called gas dynamics. So originally there was a course called gas dynamics, which considers the let's say the dynamic and motion of the every gases. Aerodynamics is a special class in gases which focuses on air, and gas dynamics is mostly for internal flows. Okay? Flow inside a pipe, flow in a duct, but aerodynamics is mostly for external flow. Okay? So aerodynamic, a study of air, external flow. Okay? So our course, we want to know how air interact with the section of the wing, with the airfoils, how air interact with it, and how are the forces, especially This big airplane, if you see a very big Airbus A300 airplane, this is a very big airplane. But that big airplane can fly and go to the sky just by its wing, okay? So the wings produce a force that overcome weight and bring the airplane from the Earth's surface to the sky. So it is our course, aerodynamic, and this is wing. A section of the wing is airfoil. A section of the wing is the airfoil. So we mostly in this class, we try to work on the airfoils first. What we do with the airfoils again, this is an airplane. There are 4 main forces on the airplane. You may know that. First, weight. The wings create an upward force that bring the airplane upward. It is called lift. And we have propeller, for example, or jet engine that produce thrust force that bring the airplane forward. And we have air resistance in the direction of motion. That is called drag force. We derive relation for all of these. We derive relation for lift and somehow drag. Aerodynamic a study of air forces on moving objects. So if you want to know about the propulsion force, the thrust force, I didn't write the name. It's good that I write. This is thrust force, studied in propulsion class. So if you have a class on propulsion, you will study the engine, the propeller, or something like that. Okay, So it is an overview of our class. Most of you are familiar with airplane. Some of you are new to the topics. But the main goal is to obtain relation. For example, this is an airfoil, okay? So, Wright brothers used this type of airfoil. Very, very thin. Very thin airfoils. Nowadays, we use such an airfoil, which is called supercritical airfoil. We want to study why the airfoil is designed in this way, or in this way. It is for transonic flight, for high-speed flight, it is for low-speed flight. So we will consider this type of airfoils, the cross-section of the wing, and find or aim. Find relation between airfoil profile and lift force. How the lift force is connected to the profile of the airfoil. Okay, we will show later how the thickness, how the camber, especially the camber. What is camber? Camber is the mean geometric line. This mean geometric line. We will show how this mean geometric line is related to the lift forces. So this force depends on this one, okay? On the camber, on the curvature of the airfoil. We will drive that relation for you. We will give you some airfoils, and you use these airfoils and drive analytically or with the computers how this shape of airfoil, how the shape of this airfoil is related to lift. I work on machine learning because now we are in the area of machine learning, okay? So I work on machine learning, and during the winter break, I try to optimize the configuration of the airfoil such that this force that brings the airfoil upward divided by this force that prevents the motion of the airfoil. So for us, an airplane flies where L over D is optimal. So for flight condition, we are seeking L over D optimal, not maximum lift, not minimum drag, but the ratio should be optimal. Okay, in the winter break, I try to work with some configuration of airfoils, and I just change the shape of it such that L over D remains optimum during the flight. During the flight. So there are some nice things that later I will show you and discuss with you. Okay, so about our class, about me that you know me, and I have a YouTube channel. The YouTube channel, my teaching on aerodynamics in other universities are available on YouTube. So you can go to my YouTube channel and watch the videos to make yourself more familiar. But the videos are very wide, so I'm very diverse. So I also taught compressible flow in aerodynamics in Embry-Riddle, but here in our course we mostly focus on incompressible flow. So for incompressible flow, so you can watch the videos on airfoil, wing, and also I record every class session, and the recording will be available on your Canvas 15 minutes after the class. So if you lose any session, you can watch the recording of the class. Okay, we have a TA for the class. I will find him. And my office hours is 3:30 to 5, Tuesday and Thursday. My office is now under construction, so I temporarily moved from Ganes 1 to Ganes 7. So I am moving between these two because some of my staff are in Ganes 1, some of them are in Ganes 7. So before coming to me, try to send me an email to be sure that I am in my office. In our class, what we will cover in this course? We will discuss conservation equation, conservation of mass, conservation of momentum, conservation of energy. We derive this equation and go to its divergence form, their integral form. So this class in aerodynamics, you get a very, very good insight on fluid mechanics. Okay, on fluid mechanics, you will understand better the governing equation. The governing equation has different forms: differential form, integral form, integrated form. Okay? So for example, in fluid mechanics, you write continuity is equal rho one A1 V1 equal rho 2 A2 V2. Okay? This is integrated form of continuity equation. Okay? Integrated. So there are two other forms: differential form and integral form. I will derive both of these two equations for you. So some part of the class you may think we go very into mathematics, but they are requirements. I am certain in no classes in your studies, in your bachelor studies, you can find advanced mathematics as aerodynamics. So the most advanced equations are in aerodynamics. So especially when you want to compute the lift force. It is much more advanced and much more complex integrals. You need to use Fourier series, okay? You need to use Fourier series to transform these to your to compute your integral. And during the winter break, I also did another job because when I was a student, I need to do all the calculation of the airfoil. I need to have the profile of this one, the profile, and then do integration by hand, conversion, and something like that. During the winter break, I wrote also an AI, a machine learning platform on Google Colab. Anyone heard the name of Google Colab? Yeah. But for what you use Google Colab?
It was for making Manhattan plots for like biology.
Biology, okay, yeah. Google Colab is a platform you can write in Python, and then you can, the Google gives you the computational resources. So I don't need to use, for example, I don't need to use my own computer to do the calculation. Google gives me the server, CPUs, GPUs for free, and if I want to use more, I should pay. But I wrote a code in Google Colab, and I share with you later. So you go to that code and enter your profile, and that code compute for you lift coefficient of that airfoil. And I put some bars for it. You can change the position of maximum camber and something like that, and then see how the lift can change. So later we will do some nice job using the new technologies, machine learning, okay? Because the machine learning is very widely used in different fields, okay? So we are as an aerospace, me as an aerospace engineer, you as an mechanical engineer who are interested in aerospace should know how to benefit from machine learning, especially when you want to optimize it. So I think that next generation of airplanes will be such that the airfoil, the wing shape changes based on machine learning data. So at any wind condition and any speed of the airplane, the shape of the wing automatically will change. So it will be maybe in 10 years, 20 years, this happen based on using machine learning. Okay, so we have conservation equation, fundamental fluid dynamic principle, elementary solution of implicit incompressible flow. We go to the potential flows equation, source, sinks, doublet, vortex, and I should tell you one thing, that every component of the lift, this force comes from vortex. Everything comes from vortex. This shape creates a vortex for the airplane, and vortex creates lift. So we will discuss this, and you will have some MATLAB coding program that, for example, I want you to put some source, sink, vortex, and see how the streamline changes, okay? So you will write some MATLAB code. In your MATLAB code, you combine source, sink, and see the profile of the flow. And finally, we have flow around airfoils and wing. This course introduced aerodynamics to MIA students, emphasizing understanding fundamental concept on low speed regime. High speed, no. Learning outcome, I wrote here the learning outcome. So one of the tasks that we will do very soon is to put an airfoil in a control volume and compute the drag or lift around that airfoil, not from the direct equation, not from equation related to the camber of the airfoil, but let me plot here. The airfoil here in the control volume, and then we have a uniform velocity here, a non-uniform here. Okay, we have a uniform velocity here, a non-uniform velocity on the right. And what we do, we compute the drag force over this airfoil from the loss in momentum equation. Because originally the momentum should be constant. But when the flow is viscous, when there is a viscous effect, originally momentum should be the same here and here. But when there is a viscous effect, boundary layer effect, momentum losses. There are loss of momentum. So the loss of momentum is drag force over this airfoil. So we will do like this, a lot of example. Okay. Or textbook, it is optional. So you are not obliged to buy the textbook. It is Aerodynamics for Engineers by John Bertin and Russell Cummings. The publisher is Cambridge. Publication in 2025. So it was published maybe the summer, the July 2025, the last version of this book. It is a very applied book, and I put the link to the book here, so you can go and, if you want, you can order the book from, borrow the book from library or buy the book. Additional references, so there are some additional references if you are interested. And there will be 2 exams. The first exam will be on 12th of March on class time. And the second exam will be the final exam on 5th of May. So the exam will not be difficult. Everything will be open. I wrote no note, but it is not correct. Everything will be open, but not AI. Expect AI, except AI, you can use anything for your exam, your note, and we will have around 6 or 7 homework in total. And the grading, okay, we will have 35% score for exam 1, 35 for exam 2, and 30% for homework. So the homework, please take the homework seriously. Homework are important and has a good percentage of your score. So, and the exam, the topics will be covered in exam 1, will not be covered in final test. So, and my exam, the student who had class with me, my exam are on Canvas, okay? I put the question on Canvas, you go to your Canvas, you write on a paper, then take a photo and upload in Canvas, yeah? Question? Is there any question? Do you have any suggestion? Do you have any recommendation, for example? Yeah?
So when you say it's on Canvas, it's an at-home test during class time?
No, in class. You should be in class, but I don't print or I don't take your notes. I just want you to upload. It is easier for me to have everything on computer. Okay, so that is all about the course. So do you want something more in the aerodynamics? So it is the course. It is, my first plan is to include some compressible part, but because there is another class on propulsion, on that class the compressible flow is covered. So in this class we just focus on incompressible flow. So, and yeah, the aim is that you make you familiar with the aerospace, aerodynamics, and some application of the aerodynamics. Okay, so I put the lecture note on Canvas, so you have the lecture note. So this is some abbreviation that I use in my lectures. And let's start with the conservation equation. So we start with the conservation equation. Okay. So I had a class in fluid mechanics. In fluid mechanics, I also tell the student about control volume. So assume we are in this room. This room, we have a lot of air around us, and there is no difference between the air here, air on the right, air on the left. So we take a sample of the air in this room as a control volume and write everything for this sample element, and then we could integrate it for our entire volume in the class or every other environment. So control volume is a sample volume, and control volume makes sense if the properties doesn't change from left to right. So if in the left we have air, on the right we have, for example, carbon monoxide, the control volume on the right is maybe different from the control volume on the left will be different from that on the right. So when everything is uniform, homogeneous, we take a control volume and we consider that. Okay? Now we want to drive for U continuity or conservation of mass equation. Okay? For our control volume, A is the surface of the control volume, area. D volume is the differential element of the volume, dA the surface element, N is unit normal. It is important. Every surface has two features. Every surface has two features: surface area, surface normal vector. Okay. Let's consider this door. Okay, let's consider this door as a surface. Okay, because if I open this door, weather or air can come in and come out. If the door is our surface, it has area equal A, normal vector N. It is the front view, it is the side view. It has, every area has the area magnitude, you can show by a magnitude, and unit normal. So A is equal area magnitude, unit normal. So area is a vector with magnitude of equal to the area, for example, of this door, and direction is toward outside of the element, outside of the element. Why area requires a vector? Because we are looking for conservation of mass. We are looking for conservation of mass. Keep this in mind. I will return back to this in a few minutes. So we have volumetric flow rate, or A dot V. Mass flow rate, rho A dot. Okay. Assume this is the surface of the air, of the door, okay? Surface of the door. This is the unit vector out toward out here, toward out. You open the door and velocity moves in this direction. No flow comes to your room. Velocity will come to your room if it has a component in the direction of n. Otherwise, velocity don't come to your room. So I open the door. By door, I mean this area, okay? This area. The unit vector is toward outside. There is no velocity outside, so there is no flow inside. There is no flow inside. Assume I open the door, the velocity outside is, I put a fan on the floor, and the fan moves the air go up. So this is the direction of velocity of the fan, air, and this is the normal vector. They are perpendicular. V dot n is 0. V dot n is 0. No flow comes to my room. But assume it is the n and it is v. All the velocity comes to my room. Assume this is n, this is v. So a component of v in the direction of n, because v or n dot v means projection, okay? Dot product means projection. If you project the velocity over the normal vector of the surface, and there is component, there will be mass, there will be flow rate. Otherwise, there will be nothing, okay? Otherwise, there will be nothing. Okay? So everything is on the dot product. If they are parallel, if n and v are parallel, maximum. Okay? So if they are anti-parallel, so you have n in this side and v in this side. So the mass will be negative. Mass goes out. Mass goes out because the angle is pi. The angle is pi. So when the angle is pi, the mass goes out. Okay, it is the schematic, very good schematic. So if you want mass coming into your room, you must have velocity component on the direction of normal to your surface. Okay? I cannot open this window. This window, normal vector is always toward out. Okay? Not toward me. Normal vector is a vector, is imaginary. Okay? We are engineers, so we imagine this is a surface, there is a normal vector to this surface. Toward out, toward the outside, if I open this window, and there is some velocity component in the direction of n, the flow goes out from this control volume. So if there is an angle between V and N, cosine of, because N dot V is equal NV cosine between N and V, okay? The cosine will be considered. So the volume flow rate is V dot N. I wrote here as a integrated equation, okay? It is an integrated equation. N dot V. The integral form of the equation is like this one. V dot N dA integral. Let me write for you here. dq dA, yeah, N dA dot V. So Q is equal V dot N dA. Then when I put hat means unit vector, a vector that is its magnitude is equal unity. So volume flow rate is equal V dot N dA, or integrated V dot, you can interchange the dot product, A N dot V, or V dot N that multiplied by A. So we can interchange the dot product. Okay. Mass flow rate is equal rho multiplied by volume flow rate, or volume flux. Rho V dot N dA. Mass flow rate. And I should keep the integral as double integral because it is over area. Over area, we use double integral. Over volume, we use triple integral. Okay? So make this one double integral. So you already learned in your fluid dynamic or other classes, Q or volume flow rate was AB. Okay? In your, it is integrated form. But in general, Q is equal A N dot B or Q is equal V dot N D A or M dot is equal rho V dot N dA. Okay? This is very simple and straightforward. If the density is constant, like our case, density goes out from the integral, and we can write m dot is equal rho v dot n dA or rho q. Okay, conservation of mass. Conservation of mass. The rule conservation of mass says that rate of change of mass inside this room is equal change of the mass due to going out from the windows and door. Okay? The room is control volume. The windows and door are control surface. Okay? Control volume is the volume. Door, two doors, a lot of windows are control surface. So rate of change of mass inside the control volume is equal mass transport through control surface. Rate of change of mass in control volume is equal transfer of mass conservation of mass, rate of change of mass in control volume, transfer of mass through control surface. Very basic, very rational. Every mind can accept it. I have this door. If I close all the windows and door and seal them very well, the mass here is conserved. Okay? But if I open, there is, for example, the air can leak from the bottom of this door. So the mass is not conserved in this room. The air may leak from the window's gap. Okay? So the mass is not conserved. So if there is no transfer, there is no change of mass in the control volume. Oh, okay. So it is our control volume and it is our control surface. Okay? CS CV. Rate of change of mass in the control volume. I take a small element here. In order to distinguish volume from velocity, I put a horizontal line over this V. It is volume. Mass in the small element on the right is rho dV. Mass in all the control volume change in mass in control volume partial T rho dV. You see, I very logically proceed. Okay? I proceed very logically. I define mass in the control volume. Mass is density multiplied by volume. Okay? Mass is density multiplied by volume. I take a very small volume, dV. You see the volume, this volume. I first take this small volume. I ask myself how much mass I have in this small volume. I call density multiplied by volume. Okay? Mass inside this volume. Then I ask myself how much mass I have in the entire control volume. This entire control volume consists of infinity of this small element. Okay? So I make an integral over this element, this rho dV, and I get mass in the control volume. But the conservation of mass says rate of change. Change, rate of change. I should add rate, because rate means partial time. Okay? Add here rate of change. Rate of change. Rate of change of mass in the control volume, partial T, triple integral, rho dV. Can anyone tell me this is equal to what? This is equal, yeah?
So
Yeah, Q. The change of mass through the windows and doors. I should put a negative here. Negative rho V dot N dA. Why I should put a negative? Because if mass is positively goes out, mass inside goes down. If this is positive, this should drop. If this is negative, it means it coming. Negative by negative, positive, this goes up. Or, what is this? This is mass through surfaces. Okay, mass through surfaces. So, I bring this to the left and we have this. I can interchange the integral and derivative. Why? So I can bring this inside in. Why? Because the integral is over volume and this is over time. So I can interchange this. So okay. Okay. So, conservation of mass equals this relation. Partial T rho dV plus rho V dot N dA is equal 0. It has two components. One component is over volume, one component over surface. So if any of them is 0, question. Assume the flow is a steady state. Which term vanish? Yeah?
Partial to time.
Partial to time, yeah. If the flow is a steady state, this vanish because when the flow is a steady state, there is no variation with time. So this vanish and this is also equal 0. So there is, when the flow is a steady state, if this room reach to an steady state, the mass here is conserved, okay? Because all the first term is 0, the second term is 0. It means that every mass that comes from the below of this door goes up from the below of the next door. So it is in the steady state because the equation simplifies. It is the conservation of mass equation. And I change the part, I bring this inside the integral, this also makes sense. Because our control volume was constant, our control volume is constant. So this room doesn't become larger or smaller. The room or is a control volume here is our room. This is constant. So the volume doesn't change with time. Okay? Take a look. This is partial time of all of this. Okay? So this is constant with time. So I bring this inside the integral and take the derivative with respect to rho only. Okay? With respect to rho only. And also, if the flow is incompressible, the first term vanishes because rho is constant. If rho is constant, the first term vanishes and just change is due to the surfaces. Okay. Let me clean here. So, conservation of mass. This is conservation of mass. Okay? I use divergence theorem. Divergence theorem convert a surface integral to volume integral. I convert the surface integral to volume integral. Is equal rho v dot n dA is equal triple integral of divergence of rho v dv. Divergence of rho v d volume. So I write continuity as or okay, what did I do? I wrote this equation, the continuity equation. The surface integral can be converted to volume integral. I converted surface integral to volume integral. Rho v dot n dA is equal divergence rho v d volume. Okay, d volume. So both integrals are known with respect to volume. I write this. What is the right side of the integral equal to? Right side? 0. If you have an integral that for any control volume give you 0, I have this integral. I didn't make any assumption about this control volume. It is an arbitrary control volume. Okay? This term is when this term inside the bracket, when integrated, is equal 0. So you have a function, an arbitrary function on arbitrary surface that when integrated give you 0. So the most rational way is to conclude that the function is 0. It was 0 that when you integrated give you 0. Okay? It is most rational way, okay? So the function was equal to 0 that when integrated give you 0. So we conclude partial rho partial t plus divergence rho v is equal 0. This is the differential form of continuity equation. This is integral form. This is integral form. Okay? These are integral form, and on the right it is the differential form. Make sense? So today we observed integral form of continuity equation and differential form of the continuity equation. Partial rho partial t plus divergence. I want you to know this. Gradient, for example, divergence of V, gradient of V, divergence of V. Okay? What else we have? You know? If I put cross here, what does it call? No? Yeah?
Is it curl?
Curl. Curl of V. Okay? Gradient of V, divergence of V, curl of V. Please do a Google search. So nowadays the life is super easy. You go to the ChatGPT, ask, please write me the difference between divergence, gradient, and curl. So these are three we use. We use divergence in continuity equation. Okay? In the continuity equation, we have divergence. In the vortex, when we go to the vortex, we will have curl. Okay? And gradient, maybe some other places we have gradient. So divergence is a downgrading function. Velocity is a vector. Okay? Then divergence or dot product. When dot product acts on a vector, downgrade the vector to a scalar. Okay? So it is a scalar. Gradient is upgrading operator. So divergence is downgrading operator, is a bad friend, calms you down. Gradient is an upgrading parameter, goes you up. So you cannot have a scalar here to get a divergence, because divergence you should act over a vector. But gradient could act over a scalar and make the scalar vector. When gradient act on a vector, what will be the result? What is the upper than vector?
Matrix.
Tensor. Yeah, tensor are matrix, but it is tensor. Tensor. So gradient of velocity is a tensor. Divergence of velocity is a scalar. Curl of a velocity is a vector. Curl is again a vector. So if V is Ui plus Vj plus Wk, divergence of V is equal partial x I plus partial y j plus partial z k dot ui plus vj plus wk. Okay? It is equal partial u partial x partial v partial y partial w partial z. It is the divergence of v. Okay? I told you in the beginning that aerodynamics is the paradise of mathematics. You see, divergence of velocity appears like this. You see it here. So we can go to the next week. Remind me to write for you curl of v and gradient of v. I will write for you next week curl of v and gradient of v. And okay. I will tell you something about divergence of velocity, the concept, next session. Thank you. See you on Tuesday.
Text your brother. 863. I'll just call him.
Thank you.
So we're now walking
So,
right.
Hello. Class. Are there?
Oh,
Trying to get a take on the
You have proposed.
no, today is the day that they're gonna. They're not
Trying
gonna
to
say.
just hang out with me.
Because everyone's like.
You were in Texas for like long.
Yeah, I don't.
I see.
Because
Does it get
I'm
cold
new
in
here.
here?
Sorry, I
Like
don't.
aerospace schools? Just checking. Yeah. Do you guys have snow?
I'm gonna grab one of take action.
Ooh, yeah, that's the topic. My mother panicked, so she made me go back early. Yeah, so I was like,
Then you like.
yeah. Yeah, mom's always panic. Anyway, I'll see you.
Oh,
so far.
Yeah, like you.
I don't know, I could see it being like a whole bunch of concept wise, probably.
You have class.
Yeah.
Two class or one?
I said one.
What? Oh.